Okay. The topic for today is time evolution in quantum mechanics, which we haven't talked about so far. Let's suppose the state vector of a system, we'll be speaking here of a pure state, so it's described by a state vector, at some initial time is psi of t0. State vectors evolve in time, so at a later time there's a different state vector, let's call it psi of t. Now, what's the relationship between the two? Well, we postulate that there is a linear relationship between the two, so that psi at a later time is given by some operator acting on psi at the earlier time. We call the operator u, linear operator. The operator u must be parameterized by the two times, the initial and the final times. So we'll write it this way, it's t comma t0. Actually, I put the final time first, t, and the initial time second in the two parameters of u. It's a convenient way of ordering the two times. So this is a postulate, actually. You can add this to the other postulates of quantum mechanics that we've talked about so far. In other words, it's to be confirmed by comparing an experiment. Now, about this operator u, it has certain properties, which are reasonable properties that we can write down. There's three that I want to mention. The first one is essentially an initial condition. It says that if the two times are equal, so let's say u of t0 comma t0, then u must be equal to the identity operator, because if you don't have any time evolution, then nothing happens to its state. The second property that we want to mention is that u is unitary. And we require this because unitary operators preserve probabilities, and this is what we expect in their time evolution. If you have a particle somewhere in space with probability 1 initially, then you expect that to be true at a later time also. Well, that is, at least unless you're creating and destroying particles, which you can do in relativity theory. But in the non-relativistic theory, that would be, you don't do that, so particle number is conserved. Actually, even in the relativistic theory, probability is conserved, and so even there you have unitary time evolution. All right. The third property that we require of u is a kind of a composition property. It says that if we take the u with final time t1 and initial time t0, and we multiply it by the u with final time t2 and initial time t1, you see this corresponds to starting at t0, evolving for time t1, then you sort of stop and think about things, and you take whatever state you have at that point as a new initial condition for a new evolution, starting at t1 and then going to t2. The answer has got to be the same thing as going straight from t0 to t2, u of t2 comma t0. It's a plausible property that this operator u should have. So those are our three principal requirements on the time evolution operator, unitary time evolution operator u. Now, let's take a look at what happens over a short time evolution, over in concept of infinitesimal time. Let's consider the operator u of, let's say, t plus epsilon comma t, where t is now the initial time, and then it's just a short time later is the final time. Let's look what happens over small time evolution. You can expand this in a Taylor series in powers of epsilon. The leading term is just given by setting epsilon equal to 0. That's u of tt, which by the initial conditions is 1. So the initial term is 1. And for the correction term, allow me to write it in the form of minus I capital omega, minus I epsilon, that's the proportion of epsilon, minus I epsilon capital omega t, and then there's higher order terms of order epsilon squared and so on that I don't care about right now. So this is just a way of writing the first order term. But of course, by Taylor's theorem, this operator omega is related to the derivatives of u. And in fact, omega of t we can see is equal to I times the partial derivative of u as a function of, let's say, t prime and t with respect to t prime, where the derivative is evaluated at t prime equals t. This is just a way of saying it's the first derivative which appears in the Taylor series. Now you'll notice I factor off a factor of I from this first derivative in the definition of omega. This is just done for convenience, but the reason for doing it is that it makes omega is an operator. It makes omega a Hermitian operator. The reason omega is Hermitian is because the original operator U is unitary. If you write down U and U dagger, you multiply them together, you'll find that omega is equal to omega dagger. So it's a Hermitian operator. I won't go through the proof of that because it's the same proof as what we did earlier for the momentum operator, I think, in the last lecture. But in any case, omega is equal to omega dagger, and it's therefore a Hermitian operator. Now, I've written omega depending on time, and the reason it does is that in this derivative, although we differentiate with respect to t prime, when we're done, we set t prime equals to t, so the right-hand side depends on t and nothing else. In other words, omega depends on t because the right-hand side depends on t as well. There's actually a special case where omega, in fact, turns out not to depend on t, and I'll go to that in just a moment, but in general it does depend on t. All right. Because of this relationship here, we say, this is just language, we say that omega is the generator of time evolution. What it means is that it's a Hermitian operator which is responsible for carrying out an infinitesimal time evolution. You want to move the state forward for a small time, you just need to act on this operator. The one, of course, is trivial, and the omega here is Hermitian. That will take you from psi at one time to a small increment in time later. So the language is omega is a generator. Now, in classical mechanics, the generator of time evolution is the classical Hamiltonian. This is all understood within the framework of classical mechanics. It involves Poisson brackets and things like that, that I don't want to go into because this is, of course, in quantum mechanics and not in classical mechanics. But in any case, the classical Hamiltonian plays a similar role. It can be used to advance the observables of the system from one time to an infinitesimally small later time by forming the Poisson bracket of the Hamiltonian of the observable. And so for these reasons, we suspect that the operator omega, which appears here, should be closely related with what we would consider the quantum Hamiltonian. We haven't defined what a quantum Hamiltonian is yet, but if I call it H, just to give it a name, the idea is that H ought to be related to omega somehow. Omega depends on t here. Since it does, we expect the H will depend on t also. So the suggestion is that the proper definition of the quantum Hamiltonian should be some relationship between these operators. Now, however, it can't just simply be H equals omega because the dimensions aren't right. H has dimensions of energy and omega has dimensions of inverse time. We fixed this up by assuming that there's a proportionality factor in here which has to have dimensions of action, and we call this proportionality factor H bar. Now, I went through a very similar means of introducing H bar in the last lecture, in which we identified the quantum Hamiltonian, the quantum momentum P as being H bar K, where K was the generator of translations. So the idea here is that momentum is the quantum operator momentum is emerging as a generator of spatial translations, and the quantum Hamiltonian is emerging as a generator of time translations. There's a question about whether these two H bars should be equal, as a matter of fact. Based on the logic I'm presenting here, why should they be equal? Well, one compelling reason just to suppose that they are is that it's clear that this is a space and time version of a relativistic transformations, where one is forming translations both in space and time. Relativity would unite these two together. And there's no way that you could achieve relativistic covariance unless these two H bars are the same. So we'll take them to be the same. There is only one H bar. In any case, this thing gives us the definition of the quantum Hamiltonian as the generator of infinitesimal, apart from the factor of H bar, it's the generator of infinitesimal time translations. All right. Now, this means that I can rewrite this expression for the infinitesimal time evolution operator as 1 minus I epsilon over H bar times the Hamiltonian H plus dot dot dot, just to rewrite the first term of this series. Before going on with quantum mechanics, let me say something about what it means when a Hamiltonian depends on time. Describe this in classical mechanics. Assume cases where you have forces that are derived from a potential. The force can be written as, on a particle, can be written as minus the gradient of a potential, which depends on position. Sometimes the potential also depends on time. We talk about time-dependent potential. I'll give you two examples of this. Let's suppose we have a capacitor plate here, like this. And let's hand, suppose we put a DC voltage across it, and we look at a charged particle, an electron in there. Now, in this case, you have a static electric field here. I guess it's pointing like this. Let's call it E0. It's a static electric field. And there's a corresponding potential, which is equal to, let me do it this way. Let me make it go the other direction. Vertically, let's call the vertical direction Z like this. And the potential is minus the magnitude of the electric field times Z times the charge of the particle minus Q like this. Okay? This is what you call a time-independent potential. The potential only depends on where you are, the Z coordinate, and not on the time. Now, on the other hand, and this would give you the force according to this formula here. Now, on the other hand, if we put an AC voltage on the capacitor, and don't make it too high a frequency, then this potential can get replaced by what I had before, but multiplied by a cosine of omega t factor. This means, of course, that the force on the particle depends not only on where the particle is, but also on the time, the phase of the wave. So this is an example of a potential that does depend on time. So this kind of a time dependence, when it occurs, doesn't have to occur because you could have a DC situation, but when it occurs, this is called an explicit time dependence. That's the usual terminology that's used for it in classical mechanics and also in quantum mechanics. It means that the observables have a dependence on time, as we say, an explicit dependence on time. All right, there's one example of it in classical mechanics. Here's another one, which won't draw pictures, so I'll just wave my hands. You probably know that when they send space probes, they try to get gravity boosts from the planets. When they launch these space probes that have left the solar system completely, they use Jupiter to get a gravity boost because it's the biggest planet and has the biggest gravity. Okay, so Jupiter is really big and the space probe is really small. So, to a very good approximation, the space probe does not affect the orbit of Jupiter. And this means that Jupiter is just following some given trajectory around the solar system, and therefore it generates what is a time-dependent gravitational field. The force that the space probe feels, or that any object feels somewhere out in the solar system, depends not only on where it is, but also on where Jupiter is. So in other words, it depends on time as well. So it's a time-dependent gravitational field. It's an example of this kind of a thing. Now, there's a lesson in this because you get an energy boost and time-dependent. The lesson is that in time-dependent force fields and also in time-dependent Hamiltonians, is that energy is not conserved. This is only conserved when the Hamiltonian is time-independent. And you can see this in the example of the gravity boost because the spacecraft gains energy from Jupiter and flies out of the solar system. This is what you get in a time-dependent force field. Likewise here, this electron can gain or lose energy in the time-dependent field. All right. Now, so that's a lesson of time-dependent Hamiltonians. Anyway, these are two examples in classical mechanics of time-dependent Hamiltonians. And we must expect that something similar to this happens also in quantum mechanics, and that's the reason why I put this H of t here, this time dependence that appears here. Nevertheless, the case in which the Hamiltonian is time-independent is, of course, very important in practice because you oftentimes have DC fields, and this is not there. And there's some simplifications that occur in that case, so I'll be talking about that later on. But right now, in general, and assume that H has a time dependence. All right. Now, this is the introduction of the Hamiltonian operator. Now, let's work out a differential equation for the unitary time evolution operator U. Here's what we're going to be interested in is the derivative of U with respect to the final time. Let's say make U as a function of t and t0, and consider its derivative as a function of the final time. In terms of regarding the final time as variable, and the initial time is fixed. Well, so I want to work out a formula for this. By the definition of the limit of the derivative in calculus, you can write this as a limit as U evaluated at t plus epsilon comma t0 minus U of t comma t0 divided by epsilon. However, the first U that appears in the numerator here by the composition law can be written as U of t plus epsilon comma t multiplied by U of t comma t0. That's this composition law number C up there. And so you now see there's a common factor of u of t comma t0 on the right-hand side in the numerator. And so this can now be written as the limit as epsilon goes to 0 of u of t plus epsilon comma t minus the identity over epsilon, that whole thing, multiplied times u of t comma t0. This. Now this remaining derivative is precisely this derivative. I can write this way as partial with respect to t prime of u of t prime comma t evaluated at t prime equals t. That's just the meaning of that first derivative there, times u of t comma t0. However, this derivative, as must appear on the board up here somewhere, is almost the same thing as omega. It's minus I omega, as you see. And in fact, you can write it in terms of h bar. This becomes minus I over h bar times the Hamiltonian, which is a function of time, times u of t comma t0. The result of this is that if I bring the IH bars over to the other side, we get a differential equation of the unitary time evolution operator with respect to the final time, considering the initial time fixed. And it's just given by the Hamiltonian multiplying onto the time evolution operator, like this. This equation can be regarded as a generalized version of the Schrödinger equation because it gives the time evolution, it's a differential equation describing the time evolution of the system. All right, so this is equations of motion. Closely related to this is another version of the Schrödinger equation, which is obtained by, if we calculate the, let's multiply by IH bar, let's calculate the time derivative of the evolution of the state vector, psi of t. Well, I'll remind you, it should still be on the board, psi of t is the u operator multiplied times psi of the initial time. So the time derivative, which acts only in the final time, is going to act only on u and not the initial value of psi. So if I do that, I'll write this over here. What I'm going to get is IH bar partial of u with respect to t times psi of the initial time t0 for the right-hand side here. However, since IH bar du dt is h times u, this becomes h times u times psi of 0, t0. However, u times psi of t0 is the same as psi of t. So putting this all together, we get IH bar d psi dt is equal to the Hamiltonian, which generally depends on time, multiplying over psi of t. Now this is an alternative version of the Schrödinger equation, which is probably more familiar to you because it's expressed in terms of Ket vectors instead of operators. But these two things are really typically related to one another. They can be regarded as two different, slightly different versions of the Schrödinger equation, the time-dependent Schrödinger equation, because it's time derivatives. Now, one final remark to make about this is to consider the special case in which the Hamiltonian is time independent. If, let's write it this way, is if the dt is equal to 0, meaning Hamiltonian has no explicit time dependence, then there are some simplifications. Because in that case, if h doesn't depend on time, then this differential equation is easy to integrate. We're trying to get the answer in terms of an exponential. It implies that u of t comma t0 is equal to e to the minus it t minus t0 times the Hamiltonian divided by h bar. This becomes the unique solution for the unitary time evolution operator, subject to the initial condition, which is part A up there. And what you see is that in this case, this is a special case, but an important special case that happens frequently. You see the time evolution operator now depends only on the elapsed time. So maybe we'll just write it this way: as u with a single parameter, which is t minus t0. In fact, usually in cases like this, we take t0 equals to 0, or we reinterpret the variable t to mean not the clock time, but rather the elapsed time. And if you do that, then you get an even simpler formula that says u of t is equal to e to the minus it h over h bar. That's the formula, in this case with a slight reinterpretation of the symbols. It's important to remember that these formulas here and here, which I'm sure you've seen before, only apply in the case in which the Hamiltonian is time independent. If the Hamiltonian has a time dependence, then you've got a much less trivial problem in trying to solve this. You just have to solve the differential equation as best as you can. Now, next I'd like to tell you about the two pictures, the Heisenberg and the Schrödinger and Heisenberg picture. These are two different equivalent descriptions of quantum mechanics. The picture that we've been using so far, well, really, we've only talked about time dependence today, so I say so far this morning, but it means so far in the course, is the Schrödinger picture. And in fact, the Schrödinger picture is what we'll use for most of the course. Nevertheless, the Heisenberg picture gives insight into certain things. It's important for certain things conceptually, and it's also well adapted to the treatment of certain problems such as the harmonic oscillator, very, very nicely solved in the Heisenberg picture. In any case, let me now tell you what the difference is between the pictures. In the Schrödinger picture, the Kets evolve in time, as I just explained. Since I want to distinguish between two pictures, let me start putting subscripts on things, and I'll put an S on it if I mean the Schrödinger picture. But let's have the convention that if I don't put any subscript on it at all, I mean the Schrödinger picture by default. So this is just what we've been talking about up to this time. The Kets in the Heisenberg picture, I'll write it as psi h with an h subscript, and this is the definition of it, was given by the unitary time evolution operator u of t comma t0 dagger applied to the Kets in the Schrödinger picture. So this is the definition of the Kets in the Heisenberg picture. It's just a definition. But you see what the definition does is that since there's a dagger on this view, what it does is it strips off the time evolution that's in the Schrödinger picture and effectively takes this back to the initial time. So as an aside, this is also equal to the Schrödinger Ket at time t0. And since this doesn't depend on time, it's just taken at a fixed time, it means that in the Heisenberg picture, the Kets don't evolve. So there is no Schrödinger equation for state vectors in the Heisenberg picture. Now, we can also transform operators into the Heisenberg picture. Suppose I've got an operator in the Schrödinger picture, which I'll call AS, and as I just explained, it frequently doesn't, but sometimes it has an explicit time dependence, which I'll indicate here as AS of t. Then the corresponding operator in the Heisenberg picture, by definition, is equal to the operator u of t comma t0 dagger on the left, and the operator u of t comma t0 with no dagger on the right. It's a conjugation of the Schrödinger operator in this manner by means of the unitary time evolution operator. Again, this is a definition. Now, the Heisenberg operator always has a time dependence. Because even if the Schrödinger operator was time independent, so there was no function of time in the middle, these two U operators depend on time, and so the Heisenberg operators always have a time dependence. In fact, this is what's called the explicit time dependence, and the time dependence that comes from the two U's is considered to be an implicit time dependence. This terminology is perhaps more transparent in classical mechanics. I'll refer you to my notes on classical mechanics if you want to understand that. But in any case, there's in effect two different reasons why the Heisenberg operator might have a time dependence, but the U's are always here, so they always give you an implicit time dependence. Well, now so this is just definitions in these two pictures. But since the Kets don't evolve and the operators do, what we now need is an equation of evolution for the operators. These are the Heisenberg equations of motion. So let's work them out just using this definition. Let's compute I h bar times the derivative of the Heisenberg operator with respect to t. What is that equal to? Well, by the chain rule, there's three terms here. There's an I h bar partial of u dagger with respect to t times a Schrödinger times u. Then there's a second term, which is I h bar u dagger times partial h, let's write it as dA Schrödinger dt times u. And then there's another term which is U dagger times A Schrodinger times I H bar partial of U with respect to T, using the three terms, chain rule for the three terms. Now, by the Schrodinger equation, the derivative of U in this last expression is the same thing as H times U. This is H in the Schrodinger picture, so I'll put an S on it. And if I take the Hermitian conjugate of it, I get a minus sign because I goes to minus I, and a reversal of these factors, U goes to U dagger. So in fact, this first term that appears here can be written as minus U dagger times H Schrodinger. I don't have to dagger that because it's Hermitian. All right? And so combining all three of these terms together, I get, if you look at the, let's do the third term first. Let's write it this way. We get U dagger, A Schrodinger, H Schrodinger times U. That's for the third term. For the first term, we get minus U dagger, H Schrodinger, A Schrodinger, U. And then for the middle term, I'll just copy. It's IH bar U dagger, dA Schrodinger dt, or I'll add a partial derivative, partial A Schrodinger dt, U. I guess there's a question of style as to whether I should use direct, straight or partial derivatives in this, but it would be better if I use a partial derivative there. In any case, these are the three terms. Now, in these first two terms, let's make an insertion of U times U dagger, which of course is just the identity. But we do that because then we see the combination U dagger A Schrodinger U and U dagger H Schrodinger U, which is the rule for converting from the Schrodinger to the Heisenberg picture. And so the first two terms become A Heisenberg times H Heisenberg minus H Heisenberg times A Heisenberg plus the third term under this copy. And the result is, you see there's a commutator here in the first term. And so I'll write this over here, is we get an equation of evolution, IH bar dA Heisenberg dt is equal to the commutator of A Heisenberg with the Hamiltonian in the Heisenberg picture, plus this last term. The last term is obtained by taking the operator in the Schrodinger picture, differentiating with respect to the explicit time dependence, and then conjugating by U dagger and U, which is what you need to go from a Schrodinger picture to a Heisenberg picture. So allow me just to write the last term, there's an IH bar in there as well, as partial of A with respect to T like this, and I'll put an H parentheses with an H subscript on it. What that means is just this combination right here. That something has been transformed into a Heisenberg picture. So the result is that this is the equation of motion for the operators in the Heisenberg picture. And this replaces the Schrodinger equation, because now there's an evolution of operators. One of the advantages of the Heisenberg picture is that it bears a closer relationship to classical mechanics than does the Schrodinger picture. In fact, in classical mechanics, there's an evolution of an operator, which we call the total time derivative of an operator along an orbit. And this is quantum mechanics here, and I'm just mentioning classical mechanics. So these are now classical observables. The time derivative is given by, first of all, a Poisson bracket of the observable with the Hamiltonian, and then the derivative with respect to the explicit time dependence. And so you see a strong similarity parallel between the quantum and classical equations of motion if you use the Heisenberg picture in quantum mechanics. So this is one of the reasons being interested in the Heisenberg picture is it gives you, it makes the connection with classical mechanics more transparent. All right. That's not the only reason for interest in the Heisenberg picture. Another reason for the importance of the Heisenberg picture, I haven't mentioned this yet, is that in relativistic field theory, the Heisenberg picture is necessary in order to obtain manifest covariance of the fields. So this is something we may see toward the end of the second semester. There's a question, yes?
This dA dt that you've written without a subscript, that's in particular the Schrodinger, right?
Here? Yeah. Yeah, this is dA dt computed in the Schrodinger picture, but then the derivative is then converted to the Heisenberg picture. That's what this formula means here. So in other words, this dA dt with H subscript is just another way of writing this. Okay. Of course, in many cases, the operators have no explicit time dependence, in which case this last term vanishes, and then the Heisenberg equations of motion are just a commutator of the Hamiltonian. All right. Now, some further remarks about the Heisenberg picture. The first and really important remark is that the two pictures are physically equivalent. Is that you can make the predictions of what experimenters will observe on the basis of theory using either the Schrödinger picture or the Heisenberg picture. They're both completely equivalent in that respect. The reason is that all predictions, experimental predictions, ultimately come down to computing matrix elements of operators. Let's say, in general, between two different states. Is that if you can compute these things, then you can make all possible physical predictions. Let's look at this first in the Schrödinger picture, in which the Kets are in the Schrödinger picture, and so therefore they depend on time. But the A's are in the A is also in the Schrödinger picture. Let's do this in the Schrödinger picture. Well, let's compare it to the Heisenberg picture, in which the Kets don't depend on time, but the A's do. In fact, let's do the Heisenberg picture first. If we take the definition of the Heisenberg Kets here, and draws by taking Hermitian conjugate of it, and likewise for operators, which is right over here, and just substitute it in, what you get for this last line here, this Heisenberg line, is that, first of all, on the right, this is going to turn into phi Schrödinger times U dagger, times U dagger, yes. The AH is going to turn into U dagger A Schrödinger times U. And then the psi H draw is going to turn into psi S Schrödinger times U, like this. And so you see the U's and U daggers cancel, and what you're left with is this becomes equal to the matrix element in the Schrödinger picture. And so, in particular, with exactly the same time dependence. So all the probabilities that one measures in quantum mechanics are given by squares of matrix elements like this, and those are the same in both pictures. Right. Now, there's one final remark about maybe a couple, two remarks. One of them is here's one remark. It's a special case in which the Hamiltonian is time independent. The HBT is equal to 0, because in that case, the unitary time evolution operator, U of t comma t0, as we've seen, is e to the minus I, t minus t0 times h divided by h bar. And the main point I want to make is this operator U is now a function of h. And so in the special case in which the Hamiltonian is time independent, the operator U commutes with the Hamiltonian. And as a result, if we take the Hamiltonian this is the Schrödinger Hamiltonian we're talking about here. And as a result, if we take the Hamiltonian in the Heisenberg picture, which is U dagger times H Schrödinger times U, if H Schrödinger commutes with U, I can bring the U dagger past the H Schrödinger, and what it cancels out with the U on the other side, and I just get H Schrödinger. So when the Hamiltonian is independent of time, the Schrödinger Hamiltonian and Heisenberg Hamiltonians are actually the same. It's a nice simplification. This, by the way, is related to the fact in classical mechanics that if the Hamiltonian is independent of time, then energy is conserved. I just mentioned it in the case of this Jupiter situation, where you have a time-dependent Hamiltonian, that energy is not conserved. But there's, in fact, when the Hamiltonian has no explicit time dependence, then the energy is conserved, and it's equal to the Hamiltonian. This is an analogous statement in quantum mechanics that when the Hamiltonian is independent of time, the Schrödinger and Heisenberg operators are the same. This is a way of saying that there is no evolution of the Hamiltonian itself. In fact, you see, let me take this equation here, and let's interpret A as being a Hamiltonian itself. And let's suppose it has no explicit time dependence, so this term goes away. Well, what do we have then? We have IH bar, D of the Heisenberg Hamiltonian with respect to time is equal to the commutator of the Hamiltonian with itself, which is 0. So in the case of the time-independent Hamiltonian, the Heisenberg Hamiltonian is constant in time. All right. Here's another one more quick remark about the difference between these two pictures. The historical remark. The vast majority of work that people do in quantum mechanics is certainly done in the Schrödinger picture. This is certainly true of non-relativistic theory anyway. But nevertheless, the Heisenberg picture came first historically. Heisenberg's paper on quantum mechanics, which was the first time real quantum mechanics was ever presented, was in 1925. But it involved the Heisenberg picture. That is to say, Heisenberg's paper concerned the time evolution of operators, not of wave functions or states. In fact, he didn't even know that there was wave functions. He sort of knew that there were operators, but he didn't really know exactly what they acted on. Nevertheless, it was possible to solve quite a few problems using this formalism. Basically, these equations of motion and working with commutators. The harmonic oscillator is pretty easy. The hydrogen atom is much harder, but was done by Pauli in really a brilliant paper shortly after that, and solved in the Heisenberg picture. It was only some months later, in 1926, that Schrödinger published his wave equation. Basically presented the Schrödinger picture. It didn't take very long for people to realize that the two were physically equivalent, and most physicists were happy to drop the Heisenberg. In those days, it was called matrix mechanics, because the operators were seen as matrices. But in any case, most physicists were happy to forget about the Heisenberg picture because they like to solve wave equations and were familiar with doing that. But nevertheless, one could argue that the Heisenberg picture not only came first, but in some senses it's actually more fundamental. All right. Anyway, that's a little bit of the history. Now, okay. Now, so far, I've been talking about Hamiltonians, but I haven't said what the Hamiltonians are. So there's a question about how do we know what the Hamiltonians are in quantum mechanics. A common way of guessing what the Hamiltonians are is to borrow them from classical mechanics. This is sometimes called the process of quantization. If you know what the classical description of a physical system is, but not the quantum one, you may use the classical description as a stepping stone or springboard for going over to the quantum description. As I say, it's called quantization for obvious reasons. However, I want to emphasize that this always involves some kind of a guess. It's not a logically deductive process. In fact, there can't be any such process for quantizing the classical system. And the reason is that quantum mechanics has more physics in it than classical mechanics does. In the case of problems in atomic, molecular, condensed matter physics, things of that sort, we know by now how to quantize the corresponding classical systems, and we know where the errors are and what additional things have to be taken into account. Most importantly, we know that spin, a phenomenon that has no analog in classical mechanics, makes its appearance in quantum mechanics. There's new physics there, in other words, due to spin. There's other cases, such as the gravitational field, where at the present time the classical description is very well known. It's Einstein's general relativity. But as of yet, some people think they know, but it's very questionable, what the correct quantum description is. So the process of quantization is not necessarily trivial. But in any case, in the kinds of common problems that occur in non-relativistic physics, we simply borrow a Hamiltonian from classical mechanics. So in classical mechanics, let's start by saying some things about classical mechanics. If the force is derived on a particle is derivable from a potential, as minus the gradient of the potential, which may depend on time, as I've explained a few minutes ago, then there is a classical Hamiltonian describing the system, and it's the sum of the kinetic energies plus the potential energy. And the kinetic energy is written in terms of the canonical momentum P. In a problem like this, the momentum P is the same thing as mx dot of mv. So the canonical and the kinetic momentum agree for problems of this sort. And this P squared here really means the square of the vector, the 3 vector squared. P squared over 2m is another way of writing 1/2 mv squared, which is the kinetic energy. So that's the first term is the kinetic energy, and the sum of that with potential energy. And so it's a guess that in problems of this sort that we might just borrow this Hamiltonian, reinterpret the symbols, P and X, instead of being classical observables, as being quantum observables that act on our PET space, and that this would describe quantum mechanics of similar situations where potential is known. A whole lot of questions arise in the process of doing this. One of them is it correct? Does it give us the correct Hamiltonian? Before you ask that, you could ask, was it correct, and even classically, that the motion could be described by a potential? The fact is that in many physical circumstances, in practice, people use potentials, phenomenological potentials. Phenomenological means that the potential energy is just it could be a fit to experimental data without peering too deeply into the deeper meaning of where the potential came from or what fundamental force laws would lie behind it. To give you an example, one could consider the collision of two atoms, and as you know, it's repulsive. It's repulsive at large distances, it may be attractive at shorter distances. And you can hope that that force could be represented in terms of a potential. Well, the books talk about it all the time as if it is representable by potential, but is it really? The answer is only in a certain approximation. You find this out if you go to a more fundamental theory. This involves Born-Oppenheimer approximation and so on. And then you find that there actually are corrections to it where the force is not completely describable by means of the potential. For another example, the interaction between a neutron and a proton. For example, in the deuterium nucleus, which you know is a bound state of a proton and a neutron, can to some degree be described by a potential, but it neglects, it's actually only a rather crude description. It turns out there are rather strong, sticking my neck out a little bit, I think it could be something like the 10% level. It's a significant level of spin interactions that are not describable by means of a potential. So the deuteron can only be described crudely by such a potential. All right. One case in which the potential seems to be fundamental is that of electrostatics, in which you write the electrostatic potential down. You know how to do this for the hydrogen atom. It's just the 1 over the distance between the proton and the electron. Isn't that a fundamental potential energy? Well, because it's based on electromagnetic theory. It's not phenomenological. The answer is, well, maybe you could say that, but it does neglect a lot of effects that are important if you look at things more carefully. It's really based on an electrostatic approximation to electromagnetism. The electric and magnetic fields that are produced by charges, and I'm just speaking of classical electromagnetic theory, electromagnetic fields that are produced by charges are only approximately given, electric fields are only approximately given by Coulomb's law. It's only when the charges are stationary that Coulomb's law is valid. If they're moving, then not only are there magnetic forces, but the electric force is not given by Coulomb's law. It's a more complicated expression. Well, charges are moving in atoms and molecules. So anything that involves electrostatic potentials that you write down, and we're going to do this all the time, it's done all the time in atomic, molecular, condensed matter physics, those are based on what I will call an electrostatic approximation. And one must always remember that it is only an approximation, and there's other corrections that need to be added. So anyway, so this is the process of quantization here involves a guess, and it also involves approximations as to the fundamental physics and the use of the potential. But anyway, having done that, we now reinterpret this as a quantum operator, and we know what P and X mean as operators. On wave functions, X is multiplication by X, and P is a differential operator. And so we get the usual Schrodinger equation as a differential equation for a particle living in 3 dimensions, which you all know. This is the differential operator acting on the wave function psi of S and T, and the right-hand side of the time-dependent Schrodinger equation looks like this. This comes from previous lecture. We worked out the action of momentum on wave functions, and in the configuration representation of this is what it is. Well, you can do it in a Kent language also. You just do the P squared over 2m plus b applied to psi of t is equal to pi h bar, partial with respect to t psi of t. In some sense, in some cases, people regard this as the Schrodinger equation. It's the one Schrodinger wrote down in his original paper. But I've erased it now. But the equation, this version of the Schrodinger equation, is in some ways is is a Ket version is actually better because it applies to many generalizations of this, multi-particle systems, relativistic effects, all kinds of other Hamiltonians. Right. All right. I'm assuming you know about separation of variables in time and about energy eigenfunctions as a complete set of states. And if you do this, then you're in, and by the way, I'll mention that the separation of the Schrodinger equation in time only works when the Hamiltonian is time independent. So I need to drop this t if I want to do that. But this would lead to an eigenvalue problem, which would be this, acting on psi n of x, gives us an energy eigenvalue E n of x, E n times psi n of x. This is the eigenfunction eigenvalue problem for a time-independent Hamiltonian, which is the only case that it's really meaningful. And this is, as you know, is used for, comes out of separation of variables and is used for expanding the time-dependent solution as linear combinations of the energy eigenfunctions. All right, now, next I'd like to introduce or check some remarks about the probability density of current in quantum mechanics. By the way, just to go back one step. As I emphasized, going from the classical to the quantum Hamiltonian is a guess. How do you know if the guess is right? You work up the physical predictions and you compare it to experiment. That's the only criterion, obviously, that can be used. Okay. Now, and if you do that, you'll find it's not going to be exactly right. There's other things going on. All right. Now, about the probability density, I explained, I believe in the last lecture, that the square of the wave function, this is something you well know, is interpreted as a probability density of configuration space regarding relating to the measurement of the position of particles across an ensemble. Today we're talking about a time-dependent wave function, so this means the probability density is also a function of time. Don't confuse this rho here with the density operator. This is a completely different object. It's an ordinary function on configuration space. One thing to say is that the normalization of the density, if we integrate it over all space, is independent of time, and in fact it's equal to 1 for all times. And this just follows by the unitarity of the time evolution operator. Unitarity preserves the norm, and that's just what this integral is the norm of the state psi. All right. Now, if you've got a quantity whose integral over all space is constant in time, such as this probability density, it doesn't mean that the quantity in question sort of moves around continuously in time. It's conceivable, for example, you could have two lumps of some quantity in different parts of space, and then abruptly some of it disappears here and reappears over there. Now, you wouldn't expect this on the basis of relativity theory, which gives you a limit on how fast signals can propagate, but in principle, some conservation of something could happen that way. Usually in physics, when some quantity that's integrated over all space is conserved, it actually evolves continuously if something moves from one place to another in a continuous manner. And that means that there's a current that's associated with it. It's a function of position and time. And then taken together, they satisfy a continuity equation, which is a statement of not only the continuous manner in which the quantity moves around, but also the total conservation. And so the question is, what is the current? Is there a current? What is it for the case of the Schrodinger equation? Well, the answer is that the current, for the case of the probability, one can write this expression down quite generally. Now, this is really only a particle moving in 3 dimensions. But that's to say, regardless of the Hamiltonian issues, or the potential, or whether there's magnetic forces, or any of that other stuff, this is the expression for the density. However, the probability current depends on the Hamiltonian in a more specific manner. For the case of the Hamiltonians up here, kinetic plus potential, the probability current looks like this. Well, first let me define a velocity operator. velocity operator is the momentum operator divided by the mass, which is what it's supposed to be for the Hamiltonian kinetic flux potential, which is P equals mv. And so it's, as an operator, it's minus psi h bar over m times the gradient. Well, J is equal to the real part of psi star times the velocity operator times psi. So the velocity operator acts on psi, and it's the real part of that. If you were going to compute the expectation value of the velocity operator with respect to some state psi, you would, of course, integrate over all space d cubed x, and you'd have psi star times the velocity operator times psi. This is what the expectation value would be. Well, you see the current involves, as you see, it's the real part of the integrand of this expectation value. You don't do the integral. So the current is not the same as the expectation value of the velocity operator. And moreover, it's real, as it has to be because the current has to be real. So now it's just an exercise using the Schrodinger equation to show the continuity equation is satisfied with this definition of J. Okay, so this much I think should be familiar to you from your first course in quantum mechanics. Let me now make a few comments about this, and then we can go. There is a question of the physical interpretation of the density. You maybe recall that I said that although we frequently use language such as the wave function of the electron, in fact what the wave function describes is the statistical properties of an ensemble more specifically than a single system. In fact, it doesn't tell us much about a single system. So in particular, this row here is giving us statistical properties of an ensemble. For example, in the case of hydrogen, you know that the electron is going to have a probability density that's concentrated, spherically symmetric, dies off exponentially, and concentrated around the proton in the hydrogen atom. Now, does this mean that the actual electron is smeared out over space in the hydrogen atom in that manner? Well, that's a single system. The answer to this is no, because if you measure an electron, measure a particle, you never find part of a particle in one place and another part in another place. And in particular, if the particle is charged, you never find a fractional charge. It's always a whole charge, and you always find the particle somewhere in space. So this rho is properly interpreted as a density, which is determined by going across the ensemble, not by looking at a single system. Well, let's look at this a little more carefully. If we did make a measurement of a single system, then it says you're going to find the electron in a particular place. What about the fact that that electron produces an electric field? If I have a proton and electron out here, that produces a dipole field, which at large distances falls off as 1 over r cubed. On the other hand, if I had the charge smeared out in a spherically symmetric manner, with a proton in the center, then the electric field of that charge distribution would go to 0. In the first place, if you just move several Bohr radii away, you're essentially outside the charge cloud. Since it's spherically symmetric by Gauss's law, the field is just given by the total charge inside the sphere, which is 0 because electron and proton cancel. So, in other words, there's a question. Does the electric field of a hydrogen atom fall off as 1 over r cubed, or does it fall off much faster than that, essentially 0 outside the charge cloud? Which is the answer? Also, if it's a dipole, you'd expect it to be a time-dependent dipole because the electron is whizzing around. Okay, just make one comment and I'll let you go. And then, as I say, there's a subtlety in this because the electron's whizzing around pretty fast. Its time scale is 10 minus 16 seconds, something like that. So if you're going to measure that dipole or measure the position of the electron, you've got to use some measuring device that acts on a time scale that's comparable to or shorter than that. That's a tall order because it's a very short time scale. If you use a measuring device that takes a longer time to make the measurement, then you're not going to see where the electron is, but you're going to see it's averaged out. And even classically, if you average it out, what you're going to get is a spherically symmetric charge distribution. You'll get something that looks like the ensemble and not the specific system. So part of the moral of this, I'll elaborate on this a little more next time, but part of the moral of this is that time averages, especially this is true for energy eigenstates, is that time averages are equivalent to ensemble averages. And so in that sense, you can speak of a single system as being described by a density, but it involves an adiabatic, has to do with time scales, and it involves an adiabatic approximation. Okay, that's all for today. Oh, wait, before you go, I want to make sure that everybody got the email I sent yesterday, because I'm really trying to straighten out this mess. I times the partial derivative of u as a function of, let's say, t prime and t with respect to t prime, where the derivative is evaluated at t prime equals t. This is just a way of saying it's the first derivative which appears in the Taylor series. Now you'll notice I factor off a factor of I from this first derivative in the definition of omega. This is just done for convenience, but the reason for doing it is that it makes omega is an operator. It makes omega a Hermitian operator. The reason omega is Hermitian is because the original operator u is unitary. If you write down u and u dagger, you multiply them together, you'll find that omega is equal to omega dagger. So it's a Hermitian operator. I won't go through the proof of that because it's the same proof as what we did earlier for the momentum operator, I think, in the last lecture. But in any case, omega is equal to omega dagger, and it's therefore a Hermitian operator. Now, I've written omega depending on time, and the reason it does is that in this derivative, although we differentiate with respect to t prime, when we're done, we set t prime equals to t, so the right-hand side depends on t and nothing else. In other words, omega depends on t because the right-hand side depends on t as well. There's actually a special case where omega, in fact, turns out not to depend on t, and I'll go to that in just a moment, but in general it does depend on t. All right. Because of this relationship here, we say, this is just language, we say that omega is the generator of time evolution. What it means is that it's a Hermitian operator which is responsible for carrying out an infinitesimal time evolution. You want to move the state forward for a small time, you just need to act on this operator. One, of course, is trivial, and the omega here is Hermitian. That will take you from psi at one time to a small increment in time later. So the language is omega is a generator. Now, but in the non-relativistic theory, that would be you don't do that. So particle number is concerned. Actually, even in the relativistic theory, probability is concerned, and so even there you have unitary time evolution. All right. The third property that we require of you is a kind of a composition property. It says that if we take the u with final time t1 and initial time t0, and we multiply it by the u with final time t2 and initial time t1, you see this corresponds to starting at t0, evolving for time t1, then you sort of stop and think about things, and you take whatever state you have at that point as a new initial condition for a new evolution, starting at t1 and then going to t2. The answer has got to be the same thing as going straight from t0 to t2, u of t2 comma t0. It's a plausible property that this operator u should have. So those are our three principal requirements on the time evolution operator, unitary time evolution operator u. Now, let's take a look at what happens over a short time evolution, over in concept of infinitesimal time. Let's consider the operator u of, let's say, t plus epsilon comma t, where t is now the initial time, and then it's just a short time later is the final time. Let's look what happens over small time evolution. You can expand this in a Taylor series in powers of epsilon. The leading term is just given by setting epsilon equal to 0. That's u of tt, which by the initial conditions is 1. So the initial term is 1. And for the correction term, allow me to write it in the form of minus I capital omega, minus I epsilon, that's the proportion of epsilon, minus I epsilon capital omega t, and then there's higher order terms, the order epsilon squared and so on, that I don't care about right now. So this is just a way of writing the first order term, but of course by Taylor's theorem, this operator omega is related to the derivatives of u, and in fact omega of t you can see is equal to space and time. Relativity would unite these two together. And there's no way that you could achieve relativistic covariance unless these two h bars are the same. So we'll take them to be the same. There is only one h bar. In any case, this thing gives us the definition of the quantum Hamiltonian as the generator of infinitesimal, apart from the factor of h bar, it's the generator of infinitesimal time translations. All right. Now, this means that I can rewrite this expression for the infinitesimal time evolution operator as 1 minus I epsilon over h bar times the Hamiltonian h plus dot dot dot, just to rewrite the first term of this series. Before going on with quantum mechanics, let me say something about what it means when a Hamiltonian depends on time. Describe this in classical mechanics. A simple case is where you have forces that are derived from a potential. The force can be written as, on a particle, can be written as minus the gradient of a potential, which depends on position. Sometimes the potential also depends on time. We're talking about time-dependent potential. I'll give you two examples of this. Let's suppose we have a capacitor plate here, like this. And let's suppose we put a DC voltage across it, and we look at a charged particle, an electron in there. Now, in this case, you have a static electric field here. I guess it's pointing like this. Let's call it E0, it's a static electric field. And there's a corresponding potential, which is equal to, let me do it this way. Let me make it go the other direction. Vertically, let's call the vertical direction Z like this. And the potential is minus the magnitude of the electric field times Z times the charge of the particle minus Q like this. Okay? This is what you call a time-independent potential. The potential only depends on where you are, the Z coordinate, and not on the time. Now, on the other, and this would give you the force according to this formula here. Now, on the other hand, if we put an AC voltage on the capacitor, and don't make it too high a frequency, in classical mechanics, the generator of time evolution is the classical Hamiltonian. This is all understood within the framework of classical mechanics. It involves Poisson brackets and things like that, that I don't want to go into because this is, of course, in quantum mechanics and not in classical mechanics. But in any case, the classical Hamiltonian plays a similar role. It can be used to advance the observables of the system from one time to an infinitesimally small later time by forming the Poisson bracket of the Hamiltonian of the observable. And so for these reasons, we suspect that the operator omega, which appears here, should be closely related with what we would consider the quantum Hamiltonian. We haven't defined what a quantum Hamiltonian is yet, but if I call it H, just to give it a name, the idea is that H ought to be related to omega somehow, and omega depends on T here. Since it does, we expect the H will depend on T also. So the suggestion is that the proper definition of the quantum Hamiltonian should be some relationship between these operators. Now, however, it can't just simply be H equals omega because the dimensions aren't right. H has dimensions of energy and omega has dimensions of inverse time. We fix this up by assuming that there's a proportionality factor in here which has to have dimensions of action, and we call this proportionality factor H bar. Now, I went through a very similar means of introducing H bar in the last lecture, in which we identified the quantum Hamiltonian, the quantum momentum P, as being H bar K, where K was the generator of translations. So the idea here is that momentum is the quantum operator momentum is emerging as a generator of spatial translations, and the quantum Hamiltonian is emerging as a generator of time translations. There's a question about whether these two H bars should be equal, as a matter of fact. Based on the logic I'm presenting here, why should they be equal? Well, one compelling reason just to suppose that they are is that it's clear that this is a space and time version of a relativistic transformations, where one is forming translations both in space. Okay. The topic for today is time evolution in quantum mechanics, which we haven't talked about so far. Let's suppose the state vector of a system, we'll be speaking here of a pure state, so it's described by a state vector, at some initial time is psi of t0. State vectors evolve in time, so at a later time there's a different state vector, let's call it psi of t. Now, what's the relationship between the two? Well, we postulate that there is a linear relationship between the two, so that psi of the later time is given by some operator acting on psi of the earlier time, called the operator U, linear operator. The operator U must be parameterized by the two times, the initial and the final times. So we'll write it this way, it's t comma t0. Actually, I put the final time first, t, and the initial time second in the two parameters of U. It's a convenient way of ordering the two times. So this is a postulate, actually. You can add this to the other postulates of quantum mechanics that we've talked about so far. In other words, it's to be confirmed by comparing an experiment. Now, about this operator U, it has certain properties, which are reasonable properties that we can write down. There's three that I want to mention. The first one is essentially an initial condition. It says that if the two times are equal, so let's say U of T0 comma T0, then U must be equal to the identity operator, because if you don't have any time evolution, then nothing happens to its state. The second property that we want to mention is that U is unitary. And we require this because unitary operators preserve probabilities, and this is what we expect in our time evolution. If you have a particle somewhere in space with probability 1 initially, then you expect that to be true at a later time also. Well, that is, at least unless you're creating and destroying particles, which you can do in relativity theory.